We're looking at the energy stored in the spring potential energy. And I already came up with this expression, derived this expression for the spring potential energy 1/2 k s squared, where s is the stretch. But I didn't really show that it doesn't depend on the path, so now we're going to do that numerically. So here's the situation that we have. I have a mass on a spring. I'm going to let it oscillate horizontally so we don't have to worry about the gravitational force. It's going to go from position 1 to 2. But it's going to go back and forth. So it's not just going to go straight from 1 to 2. It's going to go back and forth. So I can do a couple things. I can calculate the kinetic energy at the beginning. I can calculate the kinetic energy at the end. I can calculate the spring potential energy at the beginning, 1/2 k s squared, s1 squared, whatever that may be. Maybe it starts at x equals 0. And then I can calculate the spring potential energy at the end. And then that's really what I want, this change in spring potential energy, right? Because I've already said the change in spring potential energy should be the negative of the work done by the spring. So how do you calculate the work done by the spring when it goes all that way back and forth? This is where our numerical calculation comes into play. So I'm going to break the motion of this mass oscillating on a spring into small time intervals. That's how I'm actually going to model it, which I have done before, and I will link that video in the description below, so you can go back and watch that. Basically, I'm going to be using the momentum principle to model this, but I'm going to calculate the work done during each little time step. So if I calculate this vector force, F, due to the spring, and the displacement vector between where it was and where it's going to be, I can use that to calculate the work. During that tiny time interval, work is just F dot delta R. I will use the dot product, even though it's in one dimension. And then the work done will just be adding up all the works. Let's do it. I've already got it started here. So look what I did this for you. Let's run this. So here's a mass oscillating on a spring. I did it horizontally. I made the helix and everything. Okay. So it's a wall, a ball, a spring, and then down here I calculate the length of the spring. I use that to calculate the spring force right there. Again, I've done this before. I use that to update the momentum of the ball, and then I use that momentum to update the position of the ball, and then I fix the spring, and then I update time, and I do it over and over again. And then at the end, I print out the change in the spring potential energy. Right there. Just for fun, I also printed out the change in kinetic energy. Because if there's no work done, then the 0 is a change in kinetic plus a change in spring potential energy, and you notice these basically add up to 0. So yay, it's working. So I haven't really done anything other than calculate the work at the beginning and at the end. Let me run this one more time to show you that it doesn't just go and stop. It goes back and forth and then stops. Okay. So now let's calculate the work. So I'm going to come down here and say work equals 0. Because every step I'm going to calculate a little bit of work and add it to this value. So I need that value to start with. So let's put up here old x. Oops. Let's do a position. Old ball equals ball.pos. Because then down here I'm going to update the position of the ball right there. And so I need to find dr. dr is going to be the final position, ball.pos, minus the old ball position. Here's my dr. It's a vector. Now, dw is going to be equal to the dot product of f dr. And then work is work plus dw. Yeah, I don't know if this is going to work. I'm just guessing it will. Okay, so let's go down here. I don't need to print out this x1 and x2 stuff. That was just for testing. Let's just comment that out. And let's print work by spring. Is this typing too loud? I really don't know if it's going to work. You know, you never know how these things turn out. I'll save it. And I will give you this code, too. Huh. It's off. Work done by spring is half of that. Let's make a smaller time interval and see if that makes a difference. 0, and this increase the rate. Okay, yeah, that was it. So, yeah, it worked. Look at that. So, if I make this time interval even smaller, I'll get it. So, but here I have negative work done by the spring over that interval. This change in spring potential is positive. So you do get those two are the same. And the path is, it doesn't matter about the path, because this change in spring potential energy only deals with the beginning and end point. And this is actually integrating along the way. I want to make sure, let's do this, make even smaller time interval. There. Are you happy? Because I'm happy. Okay. That's pretty cool. Okay. So now we can use the spring potential energy and we can do some other stuff. I will talk to you later. I don't even know what the next video is, but it's going to be great. I'll see you later.